Thank you. So for the 2D materials perspective, I will be focusing on the hexagonal boron nitride more specifically. So in this presentation, I will be talking about some of the general points on how to reach publication quality results and calculate the binding energy of bilayer hexagonal boron nitride, and some tips and perspective on how to write a reusable script in Nexus so that you can reuse it going from one research question to another. And also based on the post-processing, I will add some more discussion on the finite size extrapolation in 2D systems specifically. So this is a slide I wanted to share for anyone who has had a chance to attend on all the sessions or missed out, and then looking for some pointers in terms of how to go through the previous sessions. So when we try to aim for a convergence of a DMC calculation for any research quality results, so we are looking at mainly two different aspects of the convergence, which is the statistical and the systematic convergence. So the statistical convergence has been covered in session 3 quite in depth, and this is an area where you should never compromise that it should be always controlled, but it is also mainly post-processing and can sometimes be system dependent, but all the tools that you need to use are mainly developed within Nexus, as explained by Jaren. So for the systematic convergence, there are several things like the time step convergence, which has been discussed previously. Although I say session 3, I think it's been touched upon almost in every session. So there is also population control, which is talked by Amanda in session 4, more in depth. Pseudopotentials by Luboš and Omar, that has been talked. And then trial wave function, I think even Paul's and Hyundok's talks today talk about this. So the localization approximation, which is an approximation that comes with using pseudopotentials inevitably, that is also talked in the same session by Luboš. And the finite size effects, I think Ray provided a good discussion on this on Tuesday in the previous session. But this is requiring all the systematic convergence, or you could also call it a systematic bias, depending on there is the energies that or other observables that you get. It requires an intuition and understanding of how DMC works. So that's where reading through the previous literature or a personal intuition helps. So what I'm showing here on the left is the binding energy curve of bilayer graphene. This is a work that was published almost 10 years ago. So I think a lot of the times people are curious about the costs of such calculations in terms of whether they are achievable or not. So considering the cost of the calculations or the computational power that has advanced in the last 10 years. So this is when you look at the literature within that perspective, that can also give you an idea what you can do, maybe using a supercomputer in 10 years ago. Maybe that kind of problem can be accessible today using an institutional cluster. So, and on the right, this is the result of the hexagonal boron nitride binding energies with respect to DFD and the DMC. So the DMC energies are here are extrapolated to the finite size limit. So you're seeing what we would see at the end of completing all the calculation that are presented in this workflow. So so this is an essential problem because as Paul and others have talked about the trying to get accurate van der Waals interaction. So this is a strong area for diffusion Monte Carlo where DFT approximations might fail and they may not exactly capture these weak interactions. So I'm going to talk about this basic script that is going through that you can find in the QMCPACK repository for the summer school. So there are mainly two scripts like which are like placed in there. So the run.py is basically constructing the items or like the nodes in the workflow. So it is like setting up the dependencies like between different elements in the calculation. But the run underscore library is mainly providing like all the settings like that you may need to use for like the different components in the calculation. For example, like whether it's being a DFT calculation or like a QMC calculation. So the workflow in here is saying that we need to converge like some of the DFT parameters in advance, which is independent from the like the workflow in here. And so for here, like you can also change like these interlayer separations based on your like a preference. So the D is standing for the interlayer separation between the hexagonal boron nitride bilayers. So we do SEF and NACF calculations on top of that. So the arrow is indicating a dependency in here. So with using like predetermined like the diagonal supercells. And then like we do like a just row like 2-body and 3-body just row optimizations using only like one of the geometries that are shown in here, but we do this like separately for like all the supercells that we like investigate. So I'll come to that why it could be important. And finally, like the MC calculations are done like which are after you have like optimized the J2 and J3 like parameters, all the DMC calculations can be performed independently. They can be submitted all at the same time. So some of the things that we looked at, like for the converge DFT parameters, is the K-point convergence. I'm sure like many of you in the audience, like who has an ab initio like a calculation background, would be able to do like these type of calculations, seeing the K-grid convergence or the kinetic energy cutoff like convergence. And for the QMC, one thing that like we are as a group suggesting people to use, especially like if they are relying on the GPU computers more, like that could be more like a memory limited, is to use the hybrid representation. So these parameters have also been like optimized independent from like the cutoff in here. So the mesh factor here is defining what the like flip spline like mesh factor like will be used for QMC calculations. So if you think of it as like in 3 dimensions, so that means you are getting an efficiency close to like 85-90%, which is like a quite significant. And if you are like, so this is a bilayer like material and most of it is composed of vacuum. So that can be like quite important so that you don't like be constrained by the memory, like if you want to study similar systems. So the contents of this tutorial is, as I mentioned, the run.py and run underscore library files. There's a README file that you can also like consult to. So the pseudo potential files and the structures that are prepared in here. So I have 7 different interlayer separations and the monolayer like structure for the hexagonal boron nitride. So the geometries that are used in here are directly scraped from bulk hexagonal boron nitride. So we added vacuum, like got 2 layers of hexagonal boron nitride from the bulk geometry and then added vacuum like around the like bilayer so that the interactions die off in that region. And so this is the like the first few lines of the run.py script. So what we are doing is that we are defining like the structure dictionary, which is like the keys are the interlayer separations or the key indicating this is a monolayer calculation versus the location of the structure files. So I'll come to that why I'm placing like a 3.0 as the first item, because in Python versions like higher than 3.7, so the dictionaries keys are always like the order is preserved. So this is going to ensure that when you like make a loop in the workflow calculation, like the 3.0 will be addressed first, so that like that will be the one that you're going to perform the J2 and J3 calculations, and then those like objects, which is like keeping the just raw parameters, will be later on used by the other geometries, including the monolayer as well. So again, this is like going back to like this K-point convergence, like simple test that I mentioned. Although the X says the interlayer distance, I'm sorry for my mistake. It should have been the K-point density, which is n by n by 1. And so we find that like this convergence is sufficient enough at like 6 by 6 by 1. So when we like form the tiling vectors and the tiling k-grid, so the tiling vector is basically standing for the supercell like size, and the tiling k-grid is the keys in here are corresponding to the tiling vector. So this says I'm going to use a 2 by 2 by 1 supercell with the 4 by 4 by 1 like a twist grid. So the idea here is that like it is simpler to see in here because these are corresponding to like a diagonal supercells and like a simple like K-point grids based on those like supercells. So the multiplications of these two like numbers in the XY plane are at least like as large as this K-point convergence that you see here, so that in each of the calculations that you run, like you're sampling the Brilliant zone with the like a similar accuracy, so that you don't get like limited by the accuracy of the calculations. And so I did that, for example, for, you may ask, why didn't I use like a 3 by 3 by 1 or like for this calculation, because the convergence is at 6. So you can also do that, but I think I wanted to be more consistent with the most expensive calculation that I have here, which is 4 by 4 by 1. So that these two, the first and the last calculation in this workflow, are using exactly the same K points, like which can provide some like systematical like benefits when you want to do the like finite size extrapolations. So as I said before, like these settings are common to all like DFT and DMC calculations. They don't depend a lot on like the system size or like the number of atoms that you have for the different elements like in your like workflow. So those like settings will be used like anywhere like in your like workflow. So as I mentioned previously, so this like the loop that is going over like the interlayer separations is controlling like the calculations that are following this like line of like stream of calculations for every interlayer separation. So in here, like what we have is this like get DFT settings, is that this is a function that is being called by the run underscore like library.py, which is importing all the settings that you need to use for the SEF and SEF and like the convergence of the orbitals, like from an NECF calculation to a like a blip spline formatting that can be run like using QMCPACK. So in here, like after getting into the interlayer separation loops, which is controlling every string in here, so this tiling vectors is actually controlling a single element like within this loop. So so in here, like we define the tile system, which is like using the tiling vector, which either 2 by 2 by 1 or like 3 by 3 by 1 or 4 by 4 by 1, and the K grids is using the dictionary that we defined earlier, like which is setting up the twist density. So so after DFT related parts are completed, so we can see that after like a basic definition of the DMC folder name, we are seeing that we are importing the QMC settings based on like the system size. So I'll come to that why like this is being important here. But so the QMC shared options were like defined as like a system size independence, and they can be reused, which are basically the hybrid representation parameters. And so once you provide this, like you will get like all the different settings for J2 and J3 calculations or DMC calculations that you want to perform like on that system. So, but we are doing this calculation like if the interlayer separation is only a specific value, which is the first like 3.0 value we defined in the initial part of the script. So it performs the J2 optimization and then uses the J2 parameters as a dependency in the J3 calculation, and then the J3 calculation is done. So this object is stored like throughout like the largest loop that is going over the workflow, and then that J3 run will be used as a dependency for all the DMC calculations that you want to perform. So so going into the run_library file, so this is where we define like all the like settings that can be imported to the like a basic workflow that we want to like use. So the starting like settings would be obviously like which computer we are using, what queues or what accounts that we are using in that computer. So I define it as a convenience to like some of you that might have access to Perlmutter. Like although I like did majority of the calculations with like an institutional cluster here at RNL, but the setup is here like done in a way that can be accessible to like more people like we're attending here. And so we are making an assumption that like the DFD settings that we use may only change like with respect to some of the subset of the settings that the DFD calculations typically use. So if you want to reuse these scripts, you can easily modify or add like more parameters that can like change from different systems that you might calculate. And so this one says that like if the machine is Perlmutter, like which in this case it is, so it will like run this calculation. So the reason for doing this is that DFT and DMC calculations typically require like much different like computer architectures or like queue requirements or like computational settings. So one ideal way to run these calculations is that you could run DFT calculations in a in an institutional cluster, for example, which would take maybe less time, like compared to like a total time or total resources. But you may want to use a computer that has a smaller turnaround. But later on, like you could transfer all the files and then change only the machine name in here so that later on, like you can continue the QMC part of the calculations without interruption, so that like you make sure that you don't like run DFT on a computer that you're like initially not like supposed to run. So some of the settings that are on the right, like which are ideal like for this hexagonal boron nitride. So they may need like some degree of modification. For example, Hubbard parameter that like Hubbard U parameter that I have not used like in this workflow, but you may want to use it for like systems that may require like transition like metals or like in general transition metal oxides that have more like localized electrons. So some of the parameters that could be like useful to mention is like this convergence threshold. I think if you're working on a much more difficult problem compared to this one, for example, that might involve like defect formation energies where the system size is very large, and the sum of the pseudo potentials that we used, if you have noticed, typically have a larger like kinetic energy cutoff. So they might be they might require more effort to converge, and like this value may not be always reachable, but you should aim to like have a convergence threshold as small as possible. So this is more stringent than like a typical DFT calculation that you would run, where you would be mostly interested in maybe like a total energies, but so similar like convergences may also be required, for example, if you were to do DFPT calculations. So it's the same applies in here, that you want to be able to like get the nodal surface of the wave function as accurate as possible, so that you require like a smaller like cutoff like threshold. So something that is like important to mention here is the symmetry tag. So depending on your system, if it has like a larger degree of symmetry, so you can benefit from it when you're doing the calculation in the SEF phase of the calculation, where like you are like, so in going from an SEF calculation to NSEF calculation, you're only needing to use the charge density that will supply the NSEF calculation. So in the DFT codes, like the reason why you are like disabling the symmetry or setting no sim equal true in an NSEF calculation, because the wave function that you generate in an NSEF calculation will be converted to the wave function that will be used in the QMCPACK calculation. So sometimes, like depending on like the symmetry of your calculation, if you enable the symmetry, the phase of your wave function, like at certain k points, might be mixed or like might be interpolated, going from like as you calculate k points that are like that can be formed like using like symmetry. So for example, an area where this caused me an issue previously was that like when you want to calculate, for example, the formation energy of graphene, and if it happens that your like k point is like the twist grid is crossing like the Dirac like point, so you will see some kind of degeneracy that has been like observed in here. So like using the no symmetry tag ensures that the phase of the wave function has been calculated more consistently for every k point that you want to use. So Ray mentioned about this, especially for the periodic boundary conditions. So it helps you get like a more consistent results, like for many of the QMC observables that you want to run. So going towards the QMC settings, like a function that I'm using in here. So this is also a very simple one, like I'm only using the system, which contains like the information on system, like the supercell, like lattice parameter atoms, and like the basically the geometry of the system. And rest is including like the hybrid parameters, and the pseudo potentials are obviously like reused everywhere. So I can give some brief information in terms of like the settings I have used for calculating perlmutter. Like so you can like modify the number of nodes that you want to use for this calculation depending on your like system or needs. But the number of threads is coming from like the fact that the architecture in Perlmutter has like a 4 GPU nodes, and every like a node has like a 64 cores per like a as a single CPU node that has like 64 cores. So dividing that by 4, which is the GPU units. So every GPU unit is like controlling like 16 CPUs in that calculation, which enables like a fair distribution of the resources between the GPU units. So going into further details, like in terms of how we choose like some of the QMC settings. So specifically for the two-dimensional calculations, I think this might have raised a number of times if you had a chance to see like a QMCPACK forums or like some of the issues that are raised in GitHub. What is the right way to choose like the LR-DIM cutoff for two-dimensional systems? So this is a parameter that is used to calculate the long range part of the eval sum interaction. As you can see, for example, so this is shown in the real space, but this cutoff is like corresponding to the like a reciprocal space. So I think the default parameter should be around 15 to 20, like if you are working with like three-dimensional systems. But in 2D systems, like this cutoff might be larger because like you're looking at a convergence around at the like a two-dimensional like a surface of a material, which may have less screening than a three-dimensional material. So some of the optimization parameters, as I explained previously, that we do like a J2 and J3 optimizations like sequentially. So the J2 optimizations are combining like a two steps where first there's a variance minimization and then energy minimization on the parameters that are optimized like from the variance minimization. And after that, we do like a J3 like optimizations on top of the optimized like J2 parameters. So this tag, this J2 init is indicating that, so there are options like whether you want to use the J2 parameters that are starting from all zeros or like some more like smarter like initialization based on RPA calculations. So there's an option to do that. I think this is helping like in terms of reaching the convergence faster for the like VMC optimizations. So although in this workflow, I keep the number of Jastrow parameters fixed, so that doesn't depend on the system size, but you can also develop routines that that tries to keep like a fixed resolution for the Jastrow parameters in the spline basis. But bear in mind that like the more Jastrow parameters that you involve in here, it may mean that like you may need more sampling, like effort to do the VMC calculation, and then you may even like introduce noise like to the Jastrow parameters that you calculate. So there must be like a good balance. So the J3 like cutoff is, I think, a typical way to define this. And it was also mentioned one of the papers that was published by like Neil Drummond, and also like maybe a typical practice in at least some of the people in the field is to use like J3 cutoff that could be on the order of an interatomic separation in your system. So the units here are in Bohrs. So what this is saying that if your cell is small enough, like then like 4 Bohrs, like which is actually like very difficult to get a publication quality like results with like a cell of that size. So just as a like a fallback, like to make sure that the parameter here is reasonable. So it puts like a maximum value of 4 like Bohrs like in terms of the J3 cutoffs that you want to use. And this is the VMC time step for like the VMC optimization. And final like thing I can talk about in here is the twist number. So when we do the VMC optimization, it is typically done on a single twist. So in this case, the twist num0 would typically correspond to a gamma twist, but you can also choose another like a twist index, which may be like a less symmetric than a gamma point. So like typically the results like are transferable between the like Jastrows that are optimized like using different twists. So here, like on the left, there are some of the like more of the parameters that we can like briefly discuss, but on the right, we are looking at the results of the J2 and J3 optimizations. So the J3 optimization has a total of 20 steps, which is the sum of like 12 variance minimization and 8 energy minimizations, and the colors indicate like the different supercell sizes. So one thing that you can see is that, so I'm plotting the energy per formula unit. So for VMC, like 3 and 4, like 3 by 3 and 4 by 4, like supercell sizes have very similar energies, but like 2 by 2 has a different energy than those. So it may indicate that wave function quality is kind of improving as you like go to larger supercell sizes. And so that is also prevalent, although it is a little bit more difficult to see. But when you look at the variance over energy ratio, as like Jaren mentioned last week, I think, is that this ratio is also like often better in the 3x3 and 4x4 like cell than the 2x2. So it may give you a hint that like maybe even though you did your best like in this like 2x2 cell, like the wave function quality may be slightly a little bit worse like compared to the 3x3 and 4x4. But yeah, the final judge of that, how like important that difference is, will be more like easier to see like when you do the like energy extrapolations, whether they deviate from a linear line that you want to extrapolate over those points. And with the J3 like optimizations, I have like a less number of steps in here. But so this is indicating that the scale is also much smaller here compared to the J2 optimization, because we are already starting like using the optimized J2 parameters in the initial set of runs in here. So this also like highlights the difference between the 2x2 and the 3x3 and 4x4 cells. So this is the one set of results for like a single interlayer separation using like 3 different supercell sizes again. So some of the parameters that we can go over here are like, so there are different approaches in terms of like how you can like set up like what kind of like sample count that you are asking from like QMCPACK to calculate for you. So one approach is to like set up a VMC like or DMC walkers per rank. So it may like come into a personal preference, but like for me this is easier to control like in terms of how much work I'm asking like from like the calculations that will be done. I think that point will be more clear as I like move towards like some of the like final slides. But what I did in here is that in terms of especially for the time step like errors that we discussed in the summer school. So the VMC time step is set to 0.3, which is like I would say like typical for like most systems that has an acceptance ratio like close to 50% for most of the materials. But obviously, like if your materials are changing, like this is like something that you can control like easily after running a VMC calculation. So for equilibration period, I think this was mentioned by Jaren in terms of getting the equilibration part like more quickly or cheaply, like, and then moving like towards the statistical like accumulation. So the first region here is the VMC part. Here is the DMC equilibration, and the last like section of the calculation is corresponding to the DMC statistics. So this equilibration part is using like a larger time step to achieve that convergence much sooner. So which you can see that like even within maybe 20 or like at most like a 30 steps, you're able to achieve like a converge DMC configurations using this time step. And I think I was like a little bit too cautious like in terms of choosing this 100 steps for the equilibration part. But this is can also be used to give you an idea about like how large the time step errors are like expected. So you can treat this as if like a separate like a DMC run that is used to calculate the DMC energies at this larger time step. So the DMC energy does not really like shift. So if you were to have a significant like time step errors, then you would be expected to see a shift between the plateau in here and the like flat region over there. But you're not seeing that. So it means that one could even use this larger time step to complete all the work. If you do it consistently for all the like calculations that you do for the monolayer and the bilayers, then your results would be expected to be very similar. So in this, like, I think in the last slide, I am talking about like the finite size extrapolation. So I think Ray mentioned about the finite size extrapolation quite extensively for like three-dimensional materials, showing that it has a like n to the minus one scaling, but it has been discussed in the literature for like a two-dimensional materials, especially this scaling is better represented like using the arguments from like homogeneous electron gas that it is supposed to be on the order of -5/4. And so based on that, I am showing on the right the finite sized extrapolation for a single like inter layer separation at three different like supercell sizes. So I'm showing two different data. On the left is the energy per formula unit for the bilayer like structure, and on the right, shown with the red, is the binding energy itself, which is the energy of the bilayer, like minus the twice the energy of the monolayer. So you can see that these two quantities like have a different rate of convergence, like to the thermodynamic limit. So obviously, if you have like only the bilayer energies, the convergence is steeper, so that, but in the case of the actual like binding energy itself, where you subtract the energy of the monolayer, you're benefiting from like a cancellation of errors, where the two body like errors that you see in this like figure are canceling out like to an important degree. But that doesn't mean that like at least in this plot there is still no like, especially this depends on the accuracy that you want to get out of like this calculation, but there is no like a single supercell that you can rely on like to use as the only supercell to like report the results. It shows that like the results definitely need to be extrapolated to get the like finite binding energy. So I think it was asked in for the previous talk in terms of like the cost of doing these calculations. So I wanted to provide some like information on that, and I can make a like a small comment about how this could be impacted if you wanted to do like a quasi-particle calculations. So these like calculations are performed on an institutional cluster here at RNL. So they are using AMD 7713 nodes. So each calculation, like all of them, are like ask for the same number of nodes from the queue, that they are all like 64 nodes calculations, and each core has 128. Each node has 128 cores per node. So this 2x2x1 supercell with the 4x4x1 twist grid took only 12 minutes to calculate, but the largest supercell with the 4x4x1 grid, 4x4x1 supercell, like needed to 220 minutes to calculate. So if you like get the ratio in terms of the wall time that is needed to do these two calculations, you have about like 18 times like a difference between the like time that is required to do these calculations. So the system sizes between these two are like obviously like 4x4x1 by like 2x2x2 is about the 4 times larger. So you can see that the ratio is like, so the textbook information that you will see that like the cost per atom, you may have already read that it scales with like n square or n cube. But I think in the real case, when you want to calculate the supercells, you're also like don't need to calculate it like using the same k-point grid as you would need to do it for a smaller supercell. So that can help you like to some degree. And I think the other point that you need to consider that the error bars, like the uncertainty in here, is like much smaller, like compared to the uncertainty that you have in there. So that means like a ratio less than 18, probably. So what we are like seeing is that like, since in this case we are doing a calculation like where we are doing the extrapolation energies per atom, And so the cost of the calculation scales with n square or n cube. So I think for the quasi-particle calculation, like this may not be as favorable as this because like for a quasi-particle like calculation or any excited state calculation, you would be typically looking at like energy differences between like two super twists. So that means that you would calculate it for a single twist, like, uh, and you need to go to like a much larger supercell sizes. So that means that you need to run like a longer, like a QMC calculation for that particular twist where you're calculating the excitation in. So, so that may have like a incur like a slightly larger like cost compared to that, but you also need to do less of a case sampling compared to like the one that you see in this slide. So like uh, I don't know the exact like figure, but I think here it is approaching more towards the n square limit, and for a quasi-particle calculation, it may be closer to the n cube like scaling. So with that, I want to say, like as Hyundai mentioned, that like there will be another session next week on running on GPUs and surrogate Hessian geometry optimization. And with that, I want to thank you for listening.
Thanks very much, Kehan. I see some clapping hands on the Zoom. So this presentation is now open for questions. I do have one at the ready. If there aren't any fresh ones, a number have been posted on the Slack and the Zoom, but I think they've largely been answered. If we've missed them, just please repost. So I'll state my question and give a comment, Kehan. So my question is going to be essentially, how are you analyzing all of these results, right? But first the commentary. Um, so there's a lot of information presented here, and there are many things that are obviously different about these kinds of calculations from the mean field calculations that we're likely all used to. So, we do acknowledge there's quite a bit here. And, if you're feeling a little bit lost, I would suggest just to go back to the molecular case or the solid state tutorial, where the ground feels firmer and, sort of restart there. And also just ask online, post an issue, anything like that. As I said, there's quite a lot that's not so common. So Kehan, here you've essentially automated computing the large fraction of a paper through all these scripts that you've put together, right? So this is much more than the quantum Monte Carlo thing, and it could be applied to DFT calculations. And it's much more reliable than running the calculations one at a time. But as I sort of touched on in my presentation, one is now going to be presented with a lot of data to analyze, and you presented a lot of beautiful graphs. How are you analyzing them and producing them? Because that's also part of the process, not just getting the data and having the calculations be quote unquote successful, but then doing the analysis.
Yeah, so I think maybe one like so for the purpose of this like tutorial, like I did not include the steps where like you could extract like the total energies or like do the finite size extrapolations like in an automated way. But I think there are ways that like that are explained in some of the Nexus tutorials in terms of how to like post-process the QMC or like a DFT energies, and then you might be able to extract the observables that you are looking for. So for the purposes of this tutorial, like obtaining the total energies, they are all like done by hand, where like you would, after the Nexus workflow tells you that the calculation is complete, like the user would go into the folder and then like analyze the total energies using QMCA. But using the tools in the QMCA. And then like again, for this tutorial, I basically like handwritten some of the like analysis and plotting tools myself, but since this is only like a smaller like fraction of data, but I think the you would need to put like more effort if you completely like want to skip on like a user yeah, user inspection of the data, like whether to see you have enough like equilibration or like some of it is already done like by Nexus to like a large degree, but this is also like the data in here is telling you that you already have accumulated by looking at visually a significant number of the statistical steps, and I saw that you don't need to like run the calculation like any longer than this, except for like if you don't want to get a smaller error bar.